All right, so I'm on page 21 in your packets. So the last thing that we're going to start about, the last thing we're going to talk about in this unit is we've talked about all the ways you can simplify rational expressions, how you can solve rational equations. Now we actually got to talk about the graphs of rational functions. All right. Now, rational function graphs are, for lack of a better term, they're pretty wonky. All right, they look weird. Like that's the best way I can put them. But there's a lot of things that go on with those graphs. So, first off, let's consider this rational function. 3x plus 1 over x minus 2. So remember, it's called a rational function because it's a ratio of two functions. More often than not, they're polynomials. So, rational functions, all rational functions, can be written in the form a of x over b of x, where a of x and b of x are functions. So, if I was looking at that 3x plus 1 over x plus 2, my a of x would be which function? The top one, 3x plus 1. What's the b of x? X minus 2. All right. Now, I forgot to have you guys do this. Take out Desmos. So get your Chromebooks out, take out Desmos. So, once you get Desmos up, here's what I want you guys to do. All I want you to do is to put these two functions into Desmos, generate a table, and get the y values for all of the given x values, just for a of x and b of x. Don't do f of x yet. All right, so for example, let's say I was doing a of x. So let's say I was doing a of x. I'm going to type in 3x plus 1. And don't forget to put equals y. Now, who remembers how to generate a table in here? So who remembers how to generate a table that goes along with a function? Nope. You click the cog wheel. And then you guys see this little table picture? If you hit that, it creates a table that has all the values of 3x plus 1 in it. And you need all of the values from -5 to 5. All right, so you can type in any x value you want. All right, so take a minute and do that for both a of x and b of x. Do you not have your Chromebook? I do. So I only want you to do that for a of x and b of x. All right, thumbs up if you're ready. Give us 1 more minute. Shouldn't take very long. Desmos is doing all the work for you. Now, if you're waiting, go ahead and do f of x2. So do 3x plus 1 divided by x minus 2. Make sure you put the 3x plus 1 parentheses, otherwise it won't do it correctly. Round. Just round to the nearest decimal place. Yeah, round to like 2 decimal places. Mm-hmm. All right, so here is what I got for both, for all three. And again, this was just copying straight from Desmos. All right, I didn't do anything fancy. I just copied what was there. Now, here's my question. If this column right here is supposed to be the same thing as a of x over b of x, do the values that you get make sense? So look at when x is -5. What's a of x equal to? Guys, it's reading a table. What's a of x equal to at x equals -5? -14. What's b of x equal to? So if I do negative 14 divided by negative 7, do I get positive 2? Yeah. So if you look right here, this is the same thing as negative 14 divided by negative 7. If I keep going down, do negative 11 divided by negative 6 in your calculator and see if you get 1.83 and it repeats. Is that what you get? Yep, works there. Do negative 8 divided by negative 5. See what you get. Do you get 1.6? Yep. Keep going for all of them. But don't do the one that says undefined yet. So what should happen, guys, when you test these is that all of these, all that's in this highlighted column is the same thing as the first column divided by the second column, not including the x column. So if you divide a of x by b of x, you get f of x. So if a of x divided by b of x is equal to f of x. Now, here's my question. Why do we get undefined at x equals 2? Because you'd be dividing by 0. Now, here's my question. If I look back at the original function, so this one right here, does that make sense when x is equal to 2 for it to be undefined? If you look at the 3x plus 1 over x minus 2, does that make sense? Why? 2 minus 2 is 0. So if we plug in that 2 for this x, 2 minus 2 is in fact 0. All right. So that is an excluded value. All right. So x equals 2 is known as its excluded value. So let's say we solved an equation and we got x equals 2. What would that be called for this? So let's say we set up an equation with this particular function. It would be extraneous. All right. Now, that is what's unique about f of 2. It's undefined. What is the cause of this result? It's the denominator, which is equal to x minus 2. And if we plug it in to the function, plug x equals 2 in, we get a denominator equal to 0, which is undefined. Now, what does that result in? Well, let's go back to our graph for a second. So I'm going to click out, I'm going to exit out of the tables and all the functions except for the one that we're looking at, f of x. So if I zoom out a little bit, this is what my graph looks like. Now, we had issues at x equals 2, so I'm going to graph that as well, just so we can see it. I'm going to graph x equals 2. So we got a straight line. Now look at what the graph itself is doing. So if I zoom out on the graph, what's happening? So what's happening? So that vertical line is the x equals 2. Does it ever cross? Does our blue graph ever cross that line? What do you guys think? It's a what? It's an asymptote. Good. So This is a x equals 2 becomes what we call a vertical asymptote. We talked about this back in unit 2 with exponential and logarithm functions. Does anyone remember what an asymptote is? Who remembers what an asymptote actually is? So the red line is a vertical asymptote. What is the red line preventing? It's preventing the graph from crossing. So in other words, an asymptote is a line that your graph will get infinitesimally close to, but it will never actually cross. All right. It may look like it does, but that's because it gets to like the thousandth of thousands of thousandths of decimal place close to it. All right, like it'll get to 1.99999999999999999. It will never hit 2, ever. So what results is what we call a vertical asymptote. So what that means is in behavior, your in behavior so if we're talking about in behavior of f of x, remember that's when we're looking at the tails. All right. Now, what is a little bit different is the tails are kind of different. All right. Meaning that we typically start with in behavior as x approaches negative infinity, which means we're talking about the left tail. And as x approaches positive infinity, we would talk about that as the right tail. And then remember, we would typically say y approaches up or down. All right. So whereas infinity is up and negative infinity is down. We learned that back in unit 3. Now, where rational functions differ, if I go back to this, is, if I zoom out a little bit more, there's not really clearly defined tails, all right? Because there's actually 4 tails if you look. So the question is, which tails do I look at? Well, in reality, our in behavior is more so the ones that are keep going straight up and keep going straight down. So it's saying that as the x values get smaller, the y values are actually approaching. No, this is not how it works. So in reality, the x values are not approaching negative infinity or positive infinity anymore. In reality, our x values are approaching our vertical asymptote, or 2. So as x approaches 2, we can look at this tail. So as x is approaching 2, that means we're talking about this tail, or this tail. Y is approaching negative infinity on one side, and as x approaches 2 on the other side, y is approaching positive infinity. Now, once we talk about horizontal asymptotes, that'll change a little bit. All right. So what we're going to do now, that'll just kind of get you introduced to it. So if I draw a quick sketch of that graph, here we have 2. We have a vertical asymptote. And then my graph looks like this. So it's just a sketch, doesn't have to be perfect. Now, let's go to you guys' journals. So go to that one foldable that I gave you in your journal. We're doing this one together as a class. If you already went ahead and did it, that's fine. You just need to pay attention. So, with rational functions, there are a lot of key features that go along with it. Yes? Wednesday. So, you guys should have your journal out, that foldable. So, there are a couple of different key features with rational functions, a lot more than what we're used to. So, we have the vertical asymptotes and wholes, horizontal asymptotes, course x and y intercepts, domain, range, and end behavior. Now, we're going to start with all the asymptotes because there's a pretty straight up way to get the asymptotes. All right. So we're going to start with vertical. We just talked about a vertical asymptote. That was in the previous example in the packet. That is a vertical line that the function will never cross. And it occurs when the denominator is in simplified form. So in other words, you have to simplify the fraction. All right, so, factor, cross stuff out. All right. So x is equal to the root of the remaining factors. So not the factor that you cross out, but the factor that remains in the denominator. You set that equal to 0, solve for x, that's your vertical asymptote. So let's look over here. Now, we've done a whole lot of factoring practice. So for time's sake, I'm just going to go ahead and give it to you factored. So this is x plus 3 times x minus 2 over x plus 3 times x minus 1. So if I cross stuff out, what's gone? X plus 3. So I'm left with x minus 2 over x minus 1. That's my simplified version of that function. Sorry, y equals, I should say. Y equals x minus 2 over x minus 1. Now, your vertical asymptote is going to come from that simplified denominator. So I'm going to set x minus 1 equal to 0. Because remember, we don't want 0 in the denominator. That's where our vertical asymptote comes from. So if I solve for x, where's my vertical asymptote at? Not just 1. X equals 1. When you write an asymptote, it has to be x equals or y equals something. You cannot just give me a number because it's an equation of a line. So x equals 1 is where our vertical asymptote is. So if I draw the graph, we're just going to draw a dotted line to represent the asymptote. That means that whatever x, we can never have x equals 1 because that's where our function's undefined. Our graph will never cross that line. Then we have a hole. Holes are kind of interesting. All right. Holes come from the factors we cancel while simplifying. And another thing to note is that a hole is a point. So a vertical asymptote is a line. A hole is a point. So you should get something xy. Whereas for a vertical asymptote, you should get y equals some number. Boys, shh. Now, the x value of the hole is when you set that canceled root equal to 0. the y values by substituting x back into its simplified form. Not the original, but the simplified. So let's try it. So if I go back over here, what was the root that I canceled out? X plus 3. So if I set, so we canceled out the x plus 3. So that's what my whole is coming from. So if I do x plus 3 is equal to 0, what's the x value of my whole at? X equals what? X equals negative 3. If you solve for x, you get negative 3. That's the x value of my whole. Now, I'm going to take this negative 3 and plug it in for both of these x's in the simplified version to get my y. So y is equal to 3 minus 2 over 3 minus 1. So what's 3 minus 2? 1. What's 3 minus 1? 2. So the whole's at the point negative 3, 1/2. Now, when you draw a hole on your graph, you draw an open circle. All right, it literally looks like your graph's going to fall into a hole. So I'm going to go to 3 and then go about halfway to 1. I'm just going to draw an open circle. That's my hole. All right, now, domain is really easy. All right, domain is always going to be all real numbers except your vertical asymptote and your hole. All right. And you can have more than one vertical asymptote and you can have more than one hole. All right. If anything cancels, that goes along with your holes. If anything stays in the denominator after you cancel everything, that's your vertical asymptote. So, and you write these exceptions as x cannot equal a number. So, for example, I would write this as so this would be x given. So the domain would be no. So the domain would be all real numbers except x cannot equal, what's my vertical asymptote again? 1. And x cannot equal what? What's the x value of the whole? Negative 3. So that's how we write our domain. You just say all real numbers except x cannot equal whatever the x values of the vertical asymptote and the whole are. Because those are the only two values that don't work. Now, we still don't have enough for my graph just yet. So that is the vertical asymptote and the horizontal, that is the vertical asymptote, the whole, and the domain. All right. Now let's look at the horizontal asymptote. Now, boys, stop. Now, horizontal asymptote, very similar to vertical asymptote. The only difference is it's a horizontal line. So it's a horizontal line that indicates where the graph levels out as x approaches positive infinity or negative infinity. Now keep in mind, occasionally the graphs may cross the horizontal asymptote. That's usually if it has what we call a slant asymptote, which we don't talk about in this class. All right? Because it's a lot harder to find and it's more of a pre-calculus thing. I mean, you asked, I answered. So, typically you'll see this as y is equal to some number. All right. Now, your horizontal asymptotes are based off of the degree of the numerator and the denominator. Who remembers what degree means? highest exponents. So degree means highest exponents. Now, the horizontal asymptote also comes from the unsimplified version of your graph. So for example, for the horizontal asymptote, you're going to use this version up here. So this one you use for the horizontal asymptote. All right. Now, how we calculate it, here are the rules. And by the way, this is also written in one of the things on your glossary entries in your journal. All right. So if your numerator is lower than your if your numerator's degree is lower than your denominator's degree, your horizontal asymptote is automatically y equals 0. If your numerator and denominator have the same degree, meaning they have the same highest exponents, what you do is you take y equals whatever the leading coefficient of the top is over the leading coefficient of the bottom. And finally, if your numerator's degree is higher than your denominator, then you don't have a horizontal asymptote. It doesn't exist. Now, there may be a slant asymptote. And again, we don't find that in Math 3. All right? Now, so just to kind of recap, if the numerator's degree is less than the denominator's degree, y equals 0. If the numerator and the denominator have the same degree, you take the two leading coefficients and make a fraction. And if the numerator's degree is greater than the denominator's, you have no horizontal asymptote. So let's go back up here and look. So if I look at my original, what is my highest exponent in my numerator? What's the highest exponent in my numerator? 2. What's the highest in my denominator? 2. So are the degrees equal, less than, or greater than? So in other words, is the numerator equal to the denominator? Is the numerator greater than the denominator? Or is the numerator less than the denominator? They're equal. So in this case, the numerator is equal to the denominator. So what we do is we take the leading coefficient. Who remembers what leading coefficient means? The number in front of the variable with the highest exponent. We take the two leading coefficients and we make them into a fraction. So that would be 1 over 1. Which 1 over 1 simplifies down to what? 1. So the way I write my horizontal asymptote is y is equal to 1. That's my horizontal asymptote. So I'm going to come back to my graph and I'm going to draw a dotted line horizontally at y equals 1. Now, from there, we can get our range. So again, range is easy because it is simply all real numbers except wherever the horizontal asymptote is and the y value of the whole. So we can write the range as all real numbers except y cannot equal whatever numbers are horizontal asymptote and the y value of our whole is at. So if I come back up here, my range, we would say all real numbers except y cannot equal. What two numbers can y not equal? So 1 and what is the y value of my whole? 1/2. So it can't equal 1/2, which is the y value of your whole, and it can't equal 1, which is your horizontal asymptote. Now, to finish the graph off, it's really nice because once you get your vertical and horizontal asymptotes, you pretty much have your graph. Because typically, your graph's going to run along where your hole is. And remember, it can't go over the horizontal asymptote, it can't go over the vertical. And then typically, it picks up diagonally from where your first graph goes. So more often than not, your asymptotes actually kind of determine what your graph looks like, determines where they curve. And again, if you don't know where, go into Desmos and look at it. All right. So that would be what that graph looks like. Last thing, in behavior. So in behavior is really easy. In behavior is the same as the horizontal asymptote if there is one. If there isn't, it's just like normal. All right. So as x approaches negative infinity, y approaches whatever the horizontal asymptote is. As x approaches positive infinity, y approaches whatever the horizontal asymptote is. And if there is no horizontal, you just check the graph to see if the ends go up or down. So, for example, if I come back up here to write out my end behavior, we always start as x approaches negative infinity, x approaches positive infinity. So your y is always going to approach for both of them your horizontal asymptote, because if you look at it, that's what your y values do. So as x approaches negative infinity, which is over here, y is approaching your horizontal asymptote. As x is approaching positive infinity, which is over here, y is approaching your asymptote. So what is that asymptote? What's the horizontal asymptote? 1. So we just say y approaches 1. So it's actually, in behavior for rational functions is actually easier than in behavior for polynomial functions, for the sheer fact is, if you know where the horizontal asymptote is, you know where the end behavior is. All right, so let's do some more examples here. And then, of course, x and y intercepts. Now, if I were you guys, x and y intercepts, plug those suckers into Desmos. Find them in Desmos. All right, but if you had to find them by hand, it occurs when the numerator is 0, you find the roots of the numerator. And then the y-intercept is you substitute 0 in for x, solve for y. All right, again, you better put it in Desmos. Like, I don't expect you guys to do that part by hand. Desmos gives it to you, so, use your resources. But, horizontal asymptote. All right, so look at this first one. What's my degree of the top? 2. What's my degree of the bottom? 2. So are my degrees the same or are they different? They're the same. So how do I find the horizontal asymptote? It's the leading coefficients, which are what? 2 over 4. So my horizontal asymptote is going to be at 2 over 4, which simplifies down to what? 1/2. So horizontal asymptote is at y equals 1/2. So that means my range is what? All real numbers except y cannot equal 1/2. Now, x and y intercept, I know you guys can go into Desmos and find it, but anyway, let's do it together. So, I have, don't forget to put parentheses, 2x squared. Is it plus 3x or minus 3x? Minus 3x, all divided by 4x squared. What was it, minus x? Minus x plus what? Minus 3. So this one's a little funky. This one will actually have a couple of vertical asymptotes. Why did it disconnect? Of course it did. Un momento. My thing did a stupid. Okay. So this is what the graph looks like. All right, this is a prime example of it possibly crossing the horizontal asymptote. That or there's a hole. There's probably a hole. Anyway, so if I want to look for my x-intercepts, I have one here and here. So what are my x-intercepts? 0, 1.5. So my x-intercepts are 0 and 1.5. My y-intercepts, let's see if I have one. It doesn't look like I'm going to have one. Why do you think that is? We possibly have a, it just means that we possibly have a vertical asymptote at x equals 0. All right, so the y-axis. So we don't have a y-intercept. In behavior, so remember that's as x approaches negative infinity, y approaches, x approaches positive infinity. Y is going to approach what for both? 1/2. Does everyone understand how that works? Now, let's just do the horizontal asymptote, the range, and the end behavior for the last one. So, what's my degree at the top? 2. Bottom? No, there is. It's 1. So, is one bigger than the other, or are they the same? One's bigger. Which one? The numerator. So, if the numerator is bigger than the denominator, what does it say? No horizontal asymptote. So if the numerator is bigger than the denominator, there's just no horizontal asymptote. Which means, as far as we know right now, our range is all real numbers because there's nothing to, exclude. So our end behavior is going to be based off of when we look at the graph. So I'm going to look at that graph really quickly. So I have x squared minus 4 divided by, what was it, x plus 3? So this one's a little funky. So my ends are here, the leftmost tail, and here, which is the rightmost tail. So what direction is the leftmost tail going in? Is it going up or down? It's going down. So it's going to approach where? Negative infinity or positive infinity? Negative infinity. What about this tail? Is it going up or down? Up. So is it going to positive infinity or negative infinity? Positive. So as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. So that one was actually an example of where you would have a slant asymptote. If you kind of look at it closely, you want to know what it is. There's actually a diagonal line along here that's not going to cross. But again, we're not talking about that. Any questions? Okay, so last thing I want to do, go back to your packets. Last thing I want to do is I just want to do 1 or 2 problems where we're actually finding everything together. So go to page 23 and let's look at number 5. So page 23, number 5. So first off, we're going to find all of our everything that does not require us to simplify first. Okay? So, what doesn't require us to simplify are the horizontal asymptote and the y-intercepts. Everything else requires us to simplify. So, horizontal asymptote. What's my degree of the top? So, the degree of the top is 2. What's the degree of the bottom? 1. So, that based off of numerator versus denominator degrees, what's my horizontal asymptote? Is the numerator bigger than the denominator? Is the denominator bigger than the numerator? Are they the same? What's true? Numerator is bigger than the denominator. So, what's my horizontal asymptote? There is not one. So, no HA. Y-intercept. All right. You just need to plug in 0 in for x. So, if I do that, y is equal to 0 minus 9, because 0 squared is just 0, over 0 minus 3. So, that's negative 9 over negative 3, which is what? 3. So my y-intercept is at the point 0, 3. Now, let's do some simplification. So the only thing I can factor is the numerator. How do I factor the numerator? It's a difference of squares. So I take the square of the first, square of the last. So this would be x plus 3, x minus 3, all over x minus 3. What can I cross out? X minus 3. So this will just be x plus 3. So first off, do I have anything left in the denominator? No. So if that's the case, we don't have a vertical asymptote. So if you don't have anything left in the denominator, there's no vertical asymptote. However, don't I still have a hole? Yes, because I crossed something out. If you cross something out, you automatically have a hole. So my hole is going to be at wherever x minus 3 equals 0 is. So x minus 3 is equal to 0. What's that going to look like? X will equal 3. So that's the where it goes there. That's the x value of the whole. The y value you plug back into the simplified version. So y would equal 3 plus 3. So y is equal to what? 6. So I have a whole at 3, 6. So my x-intercept is, if I take the current numerator and set it equal to 0, that's where my x-intercept is going to be. All right. So if I set x plus 3 equal to 0, I have an x-intercept where? X equals 3, or negative 3. So my y-intercept is at negative 3, 0. Domain. What's my domain? All real numbers except what? What's the only x value that can't happen? Right, x equals 3. X cannot equal 3 because that's where we have a hole. Now, I know they don't ask us this, but what about range? Nope. Range will be what? All real numbers except what? X, not x. Y cannot equal what? Six. That's the y value of the whole. Now, before we graph, let's go to Desmos and check our work. So I have x squared minus 9 all over x minus 3. So it actually turned out to be a linear graph. However, so the y-intercept is at 3. X-intercept is at negative 3. All right, so we were right on those fronts. Now, real quick, we're going to check the point 3,6. So I'm just going to write in where x is equal to 3 because that's where it cancels. Do you see how that doesn't mark the point of intersection? So if I zoom in, guys, do you see how it doesn't mark the point of intersection like it should? Why do you think that is? Because look, it's undefined. If you hold it, it has to be like really close. But do you guys see how like it'll go undefined right there? It actually does have the hole. So even though it looks like it's there because they don't graph the hole, it's actually not there. So if I graph this, I have my x-intercept at negative 3, my y-intercept at 3, and at 3, 6, I have a hole. And then everything else just looks like a linear function. So this one doesn't even look like a rational function. It looks like it's linear. Now, here's my question. Is this a continuous function or does it discontinue? So discontinue means it breaks or it jumps. It's discontinuous because of that hole. The hole is where it breaks. All right, so this is discontinuous. Any questions on that one? Aiden, really? Do I need to do another one? Or are you guys pretty good on like finding these key features? Guys, stop. All right, so you guys got a solid 25 minutes until class ends. There's a new Delta Math. Make sure you're working on that.